In this video, we are going to talk about the distance between two lines. So we want to determine the distance between two lines. That is the length of the shortest line segment connecting the two lines together. And so that shortest line segment between the two lines is going to be wind up to be perpendicular to both lines. Okay. Um, so um, if I've got this situation here, if I've got a point P1 on a line L1 that is parallel to D1, so that would be the point on the line and the direction vector of the line, and then P2 be a point on line 2 parallel to direction vector 2, D2, that would be the direction vector for line 2. If the lines L1 and L2 are not parallel, okay, then the distance h between the two lines is going to be given by this formula right here. So the distance between the two lines is going to be the vector from P1 to P2 dotted with the cross product of the direction vectors. Okay, and then you take the absolute value of it and then divide by the magnitude of the cross product of the two direction vectors. Okay, so that's going to give you that formula. So first thing is that this formula is only going to work if lines 1 and line 2 are not parallel to each other. If they are parallel to each other, then all you need to do is to pick a line on the first line and use the formula that we talked about in the previous video to find the distance from that point to the other line. So you don't need this formula if they're parallel. If they're skew, though, then you can use this line. Okay. So where does this formula come from? Okay. So basically, this formula, all it really is the orthogonal projection of the vector P1, the vector from P1 to P2 onto the cross product of the direction vectors. Okay. All right, and so that's where this formula comes from, and we'll run through that. So the question is, why would you do that? Well, remember that shortest line segment connecting two lines is going to be perpendicular to both lines, right? So that would mean that you can get the direction of that line segment by taking the cross product of the direction vectors, right? That when you do the cross product of the direction vectors, that will give you a vector that's orthogonal to both of those direction vectors. And so therefore, since that line segment is also perpendicular or orthogonal to both those lines, that cross product, right, is going to give you the direction of that line segment. All right. And then it's just a matter, once you find that direction, then the other thing you need is the magnitude of the vector, right? And so that magnitude of the vector is going to come from taking the orthogonal projection and then taking the magnitude of it. All right, so let's take a look at how that would go just real briefly here. Here, right, I have the projection of the vector from P1 to P2 onto the cross product. All right, and so this is, and I'm taking the magnitude of it. So here I've just replaced this with the formula for the orthogonal projection, right? I'm projecting P1, the vector from P1 to P2 onto the cross product, right? So that's going to be the vector from P1 to P2 dot the cross product divided by the dot of the cross product with itself times all that scalar multiplied times the cross product. So this is just replacing this with the formula for orthogonal projection. And now we want to take the magnitude of all this, right? So all of this is a scalar, right? So the magnitude would be the absolute value of the scalar. So that's why I have these absolute values on top. On the bottom, right, when I dot a vector with itself, it's just the magnitude squared. So that's why I have it written out like this. And of course, the magnitude is going to be non-negative, right? So the absolute, I don't need extra absolute value bars down here. Then the times the magnitude of this vector here. So that's again where this magnitude of the cross product is coming from. So this would be the absolute value of this scalar out in front times the magnitude of this vector. And then one of these factors will cancel out, okay? And that leaves me with just this top part of this fraction here and one of these magnitudes of the cross product in the denominator, okay? So, so that's where the formula comes from. It's just the orthogonal projection, right? But geometrically, why does that work? If you look at the graphic in the textbook, to me it's a little bit confusing because it's drawn, it's on a page, right? So it's just it's really 2D, and it's trying to simulate, you know, three-dimensional settings, but the graphic in the textbook is a little misleading to me. It doesn't really help to explain the geometry of it. So I am going to leave the explanation of that until the next section when we talk about the distance between two parallel planes, because this formula geometrically, you can see, you know, we'll be able to explain it in those terms, and I think it's an easier explanation there. Okay. All right, let's run through an example. All right, so we want to find the distance between these two lines. All right, and so I'm going to go ahead and open this up in a new tab. All right, so there are our two lines, 0, 1, 0, 1, 0, 0, 0, minus 1, 1, and 0, 1, 1. All right. All right, and remember what we're after, right, is h equals the absolute value of the vector from P1 to P2 dotted with the cross product of the direction vectors. And then divided by the magnitude of the cross product. All right, so that's what we're after. Okay, so P1 is the point on line 1. We're just going to use this point right here, 0, 1, 0. Remember, you can get a point by plugging in a value for the parameter. So if you plug in 0, you get 0, 1, 0. Remember, that is a vector that points to the point on the line. And so P2 then would be 0, minus 1, 1. All right, and then we would do the vector from P1 to P2. All right, and so that's going to be terminal minus initial, so 0. Negative 1 minus 1 is minus 2, and 1 minus 0 is 1. Okay. Next up, we need to take the cross product of the direction vectors, right? So the direction vector D1 is 1, 0, 0, right here. And D2 is 0, 1, 1. All right, so we need to take the cross product. So I, J, K, I, J, and then D1 is 1, 0, 0, and D2 is 0, 1, 1. Okay, and now we are going to go ahead and multiply those out. So again, I times 0 times 1, that's just 0. That goes right here. J times 0 times 0, that's just 0. K times 1 times 1, so that's K, 1K. And then go back the other way, that's 0. That one's 0. I, 0 times 1. J times 1 times 1 is j. All right, and so it's the stuff on the right minus the stuff on the left. It's going to be k minus j, right? And so that is going to be the vector. There's no I, so that's 0. With j, it is -1, and then with k, it is +1. So there is d1 cross d2 here. And the magnitude of d1 cross d2 is 0 squared plus -1 squared plus 1 squared, which is the square root of 2. All right, so now we are ready to go back over here to our formula. All right. P, the vector from P1 to P2 is 0, -2, 1. We are going to dot that with the cross product, which is, where are you at? 0, -1, 1. Take the absolute value of that, and then we are going to divide that by the square root of 2, which is the magnitude of the cross product of the direction vectors right here. All right, so let's carry that out. When we do the dot product, we get 0. 0 times 0. -2 times 1. -1 is +2. 1 times 1 is 1. Okay. And then all that divided by square root 2. So we get 3 over square root 2. And that is the distance between the two lines.